welcome to a brand new edition of I Love Chemistry with me, Dr. Winchester. Today we're going to be going through some thermodynamics questions for the A2, AQA A2 syllabus. You should be able to go onto KLP if you're a working student and download a set of questions and also a mark scheme for it. So what I would suggest you do is do the set of questions and then watch the video as you go through it, make any corrections you need to, and then mark it in total and give yourself a percentage. So let's just go straight on with question 1. So question 1, part A, write an equation including state symbols, I would always underline that, for the reaction that has the enthalpy change equal to the lattice dissociation of the enthalpy of magnesium chloride. Okay, so first things first, get the formula of magnesium chloride right, and they're asking for lattice dissociation. So that means that we're going to be dissociating the lattice, so we're going to start off with the solid and then we're going to make it into its gaseous ions. Okay. So Mg is 2 plus in the ionic state, so it's going to be MgCl2 as a solid, it's in its standard state. We're going to be dissociating that ionic compound, flying the positive ions away from the negative ions, completely overcoming the ionic bonding to make gaseous ions. So it's going to be going to magnesium 2 plus gaseous and 2 Cl minus gaseous. Have I done everything it says? I've got the equation, I've got the state symbols. The enthalpy change should be equal to lattice dissociating enthalpy. Because I've dissociated 1 mole of this magnesium chloride, so there's always going to be 1 mole of something in an enthalpy change that's equal to a lattice dissociation enthalpy or something like that. So for here it's 1 mole of the magnesium chloride. So on to part B. Explain why the lattice dissociation enthalpy of magnesium chloride is greater than that of calcium chloride. Okay, so first of all, spot the difference between magnesium chloride and calcium chloride. Well, both of them have got 2 plus ions attracted to negative ions. The chloride is exactly the same, so it can't be anything to do with that. So it must be to do with something to do with the magnesium and the calcium, those ions having a different ionic bond strength with the chloride ions. So look at them on the periodic table, you see that magnesium is in period 3 and calcium is in period 4. So magnesium ion is smaller than your calcium ion. Okay, so if let's look at this. This is 1 ionic bond. Look at it next to the chloride ion. So those ionic spheres touching each other, and here the distance between the centres of the ions is going to be larger with a larger ion than it would be here, whereas the charges are exactly the same for magnesium and calcium. So this is going to be a stronger ionic bond because the attraction is stronger if the distance between the ions is smaller. The concept I would use to answer this question would be that magnesium is more charge dense than calcium. The 2 positive charge, if you like, the whole thing is overall 2 positive, is spread over a smaller volume than for the calcium. So it's more charge dense, so therefore it forms stronger ionic bonds. It's more attracted to the chloride ion, so therefore more energy is needed to overcome the lattice. A similar question here. Explain why the lattice dissociating enthalpy of magnesium oxide is greater than that of magnesium chloride. That's question C. So now let's look at magnesium oxide and magnesium chloride. Again, spot the difference. Magnesium oxide made up of Mg2 plus and O2 minus, whereas magnesium chloride made up of Mg2 plus and Cl minus. Now here the magnesium is the same, so it's not going to be anything to do with that. So we're looking at the difference between oxide versus O2 minus and Cl minus. And again, charge density is going to be our key fundamental concept to think about here, because if something's more charge dense, it's going to attract the oppositely charged ion more. It's as simple as that. So oxide and chloride, well, oxygen is in period 2, so the oxide ion is like a full period 2 electronic configuration, and it's 2 minus charge compared to chloride, which is in period 3, so bigger, and it only has a 1 minus charge. So here, which is more charge dense? The oxygen is definitely more charge dense than the chloride because it's got more charge. It's a greater charge on the iron. That's the biggest thing to mention, I would say, for the mark scheme. It's got a greater charge on the iron spread over a smaller volume. It's definitely more charge dense. So oxide is more charge dense than chloride. Therefore, the ionic interactions between magnesium 2 plus and oxide ion is stronger than that of magnesium 2 plus and the chloride ion. Therefore, the lattice enthalpy, lattice associated enthalpy is going to be bigger because more energy is required to break up that lattice. So if we just turn over the page, go to part D. So I just need to scrub this out because we're going to be doing a little bit of a enthalpy, a bit of a Hess diagram for this. So when magnesium chloride dissolves in water, the enthalpy of solution is minus 1.5 kilojoules per mole. The enthalpy of hydration of the chloride ions is minus 364 kilojoules per mole. Calculate the enthalpy of hydration of magnesium ions. We also actually need the lattice enthalpy of magnesium chloride for this, because the enthalpy of hydration data talks about hydrating a mole of gaseous ions into aqueous ions and dissolving into a mole of aqueous ions. So we need to come from moles of gaseous ions. And how do we break up a mole of a solid, ionic solid into gaseous ions? We need to know the lattice enthalpy because that's the process that we're going to do, the lattice association enthalpy. And they've told us that before in the question, right at the top of question 1. Magnesium chloride, lattice association enthalpy is plus 2493. Okay, so this delta H for dissociating this lattice is plus 2493. And let's make up our little cycle and see if we've got enough information in to work out our what we want to know, which is the enthalpy of hydration of magnesium ions. Okay, so that's one piece of data we have. To draw out our little cycle, I think you want to start off with, well, we have enthalpies of solution. Now, enthalpies of solution, minus 155, quite a small change. They can be positive or negative, they can be exo or endothermic, depending on a balance of these enthalpies of hydration versus the lattice enthalpy of the thing, whichever's greater in magnitude kind of dominates and makes the enthalpy of solution either exothermic or endothermic. So let's start off at our level of having 1 mole of magnesium, we are talking chloride, yeah, chloride solid. Every level in a Hess diagram, put the state symbol, because changing state takes energy, or gives out energy depending which way you're going. So you've got to have state symbols in there, because it's very important, or else energy would. We're not telling you exactly what level of energy we are if we're not specifying what state we're in. We know the lattice enthalpy, so let's just do that first. This is huge and positive. We're going to dissociate this ion. So really here, our biggest arrow should be going from here to here, going to make 1 mole of magnesium 2 plus gaseous ions, and completely ripped apart this lattice, 2 moles of chloride, gaseous ions, and that change corresponds to plus 2493, because I've done it for 1 mole, so that change is fine. Now, in 2 steps, we can hydrate first the magnesium ions, for example. You could also do the chloride first, whichever you prefer. Make them aqueous, hydrate those. Do 1 step at a time though, so just if we've done this change, then nothing happens here, so just leave them as they are, but write them in, 2Cl minus gases. You've got to have everything written at every step. Now this is the enthalpy of hydration of magnesium 2 plus, and I think we have that value. No, that's the value we're looking for. Okay, so we just leave that in as it is, and then what we can also do is hydrate the Cl minus ions to give you 2Cl minus aqueous and Mg2 plus aqueous. Getting a bit messy here, I'm afraid. I haven't touched this one, but I've done 2 moles of chloride ions gaseous getting dissolved to make 2 moles of chloride ions aqueous. So I have 2 times the enthalpy of hydration of your Cl minus ions. I think I'm given that data. So that should be equal to 2 times minus 364. Which would equal minus 728 kilojoules per mole. And I'll change from here to here, maybe drawn a little bit too big actually. If I've got 1 mole of solid and I'm making 1 mole of aqueous solution, well, I'm splitting it all up into its aqueous ions. That is the same as enthalpy of solution. So going from here to here is the enthalpy of solution of magnesium chloride, which they give us as minus 155 kilojoules per mole there. I'm not going to put units in just for quickness, although it's quite nice to put the units in. It's definitely important to make sure the units are right. Final calculation then, Hess's law says that it doesn't matter which way what route I take, as long as I go from the same starting products to the same finishing products, the enthalpy change will be the same. So I want to go from, and this is quite nice to do sometimes, I'll write a little S in a circle and write a little F in a circle. I want to go from start to finish. I want to go with this arrow here. So delta H hydration of Mg2 plus equals, going against the arrow first. I need to go from here to here, so I'm going to go around here. So I need to go against that arrow. So minus, and I always like to sometimes actually put, I always like to put, what's this in the brackets after the minus tells me I'm going against the arrow, and then plus 2493, because that's the value I'm using. Then I'm going with this arrow, so it's plus minus 155, and then I'm going against this arrow, so it's minus, because I'm going against it 2 times, well, I've done that math, so it's minus a minus 728. Okay. And just have a look at them and make sure they make sense. Minus a plus, well, I'm going down, so that should be negative. Plus a minus, well, I'm going down, so that should be negative. Minus a minus is plus, well, that makes sense because I'm going up. So all of that seems to work, and then we just do the maths, and that'll get you the right answer. Okay, just rub that out. Good time. So if we continue on, energy is released when a magnesium ion is hydrated because magnesium ions attract water molecules. Explain why magnesium ions attract water molecules. You may use a label diagram to illustrate your answer. I would always put one down if they've said that. It seems a bit stupid not to, because you could get 2 marks probably just for a label diagram here. But you do the label diagram and the explanation to be safe. So you've got your magnesium ion. Now, it's going to be attracted to water. Water's a polar molecule. Water has oxygen and hydrogen. Oxygen is more electronegative than water, so it pulls the electrons in the bond slightly closer towards it, so we say that's delta negative, and the hydrogens are delta positive. So there's basically electrons in these bonds are being moved slightly more towards the oxygen, so it's slightly negative, and these ends are slightly positive. Okay. Now, so which bit of this water molecule is going to be attracted to the magnesium? Well, the water end, the oxygen, sorry, of the water. Okay, it could be one of the lone pairs. Actually, in reality, one of the lone pairs on the oxygens could have an interaction with the magnesium ion directly, but the point that they want to get into this equation is the fact that it's polar and it orientates itself, so the partially negative bit is interacting with things. So maybe with the positive ion. So I would say here, attraction between the negative pole of water versus with the positive ion. Okay. Energy is released because the hydrogen might attract. Explain why magnesium ions attract water molecules. So I think we've pretty much covered that one. Let's make sure. Let's have a look at the mark scheme for this one. Water is polar. First mark. So magnesium 2 plus ion, positive ion charge attract the negative, the partially negative bit on the water molecule. So that's all fine. Suggest why a value in a data book value for the enthalpy of solution of magnesium oxide is not found. So why might you not be able to dissolve magnesium oxide into its constituent ions? So if that's might be quite a tricky question. So just have a think about it. Well, if I'm having a question like this, I'd write down the process in an equation and see if anything comes to me. So really, what we're saying then, magnesium oxide is MgO solid, and if I was going to dissolve it and have an enthalpy of solution, I should separate the constituent ions into their hydrated version. So magnesium 2 plus aqueous plus oxide aqueous. And actually, I don't really know of that many forms. Oxide aqueous doesn't look familiar to me, so it's something to do with that. And actually, it's because this will react with the water to make 2 hydroxide ions. So really, when you do this, when you dissolve magnesium oxide, it doesn't dissolve straight, just like this. It reacts with the water instead to make magnesium hydroxide. So that's the key to the question there. So if you didn't know that straight away, if you didn't know, oh, remember magnesium oxide reacts with water, if you haven't remembered that, look at this and maybe that'll be a clue for yourself. Okay, I don't see that, so maybe, but what do I know that's got oxygen in it? Oh, I know it's hydroxide ions exist, so that might help you get towards it. Okay, but for any tricky question, just write down what you know and then see if it comes out. Okay, we'll just go quickly on to question 2. This is now a question about entropy and Gibbs free energy. You've got a data, you've got a bit of entropy data and some enthalpy of formation data, and you've got this reaction of nitrogen monoxide with half an oxygen molecules, or half a mole of oxygen molecules to give nitrogen dioxide. So goes to NO2 gas. Calculate the enthalpy change for the reaction. So I want to know what delta H is, delta HR if you like, for the reaction. But I've got enthalpy of formation data, so I could form all of these things from their elements. Oxygen is its element in the standard state, so that's not going to correspond to a change. What would be the elements that make up both sides? Well, it would be N2 gas, and O2 gas. It'd actually be a half an N2 gas to get it balanced, and O2 gas. To make up both reactants and products, it's a balanced equation. So, one enthalpy change would be from the elements in their standard states to nitrogen monoxide, so that would be the delta HF of NO. This change is 0 because the other half mole of oxygen is just going to half mole of oxygen gas. There's no change there. There's the half mole of oxygen gas going to half mole of oxygen gas, so they're going to be on the same level. And then the other change is making up the product NO2 from half an N2 gas NO2, so that would be the enthalpy of formation of NO2. I want to go from start to finish, so I'm going to go against these arrows and with that arrow. So delta HR equals the negative of this enthalpy of formation of nitrogen monoxide, which I'm told is 90, negative of plus 90, and then plus, because I'm going with this arrow, whatever that value is for nitrogen dioxide, which is 34 kilojoules per mole. So I should just be minus 56 kilojoules per mole. That should be my delta H. Calculate the entropy change for the reaction. So let's just change this now into minus 56. If I'm doing the entropy change for the reaction, I need to consider the entropy values. Now, everything has an entropy value, and nothing has no disorder at all. So all of these will have a value. It's not like we're going from the standard states here to anything. Everything's got an absolute entropy value from this kind of hypothetical zero entropy. But you can almost think of it like a Hess anyway. You've got an entropy value from this zero. I wouldn't suggest you do this when you're working, but it might be a nice way to think about it. nitrogen dioxide is 240 joules per Kelvin per mole above this hypothetical 0, or no disorder, perfectly ordered state. Oxygen, and we've got 1 mole, so that's per 1 mole, isn't it? Oxygen, for 1 mole of oxygen is 211, but I've only got half a mole there. So the entropy for half a mole would be a half times oxygen's 211 joules per Kelvin per mole. And nitrogen monoxide would be 1 mole, so 205. So the delta S here is going to be going from here to here, so you can think of it going that way as well. So it's going to be what you end up with minus what you started with. So delta S is the entropy of the product, take away the reactant. So 240, but we didn't start off at 0, we started off at level already. So take away a half times 211. And you're also taking away 205, which will give you a negative answer of whatever. So this is going to be 105.5 there. 240 take away 205, if you like, is going to be 35. 35 minus 105.5 is going to be minus 70.5 joules per Kelvin per mole. So that's the final answer, so that's delta S. Now calculate the temperature below, its last one we'll do, I think. Calculate the temperature below this, which this reaction is spontaneous. We have the delta H, we have the delta S, and we know our equation for Gibbs free energy, which tells us whether a reaction is going to be spontaneous. If it has a negative delta G, that means the reaction will be spontaneous. Doesn't mean it happens quickly, it just means it can happen. It's thermodynamically allowed. So the temperature below which this reaction is spontaneous, we're looking for the tipping point of being non-spontaneous to being spontaneous. So we want delta G to be 0. That's the first point at which it's going to start to become negative. So delta G equals delta H minus T delta S. 0 equals delta H minus T delta S. Delta H therefore equals T delta S. The temperature is going to be delta H over delta S, as long as we get the units right. Delta H here is minus 56 kilojoules per mole, and delta S is minus 70.5 joules per Kelvin per mole. So let's change that into kilojoules, say, by dividing it by 1,000. So minus 70.5 divided by 1,000, and then now it's in kilojoules per mole. So we do the maths and make sure that makes sense. Calculator. Minus 56 divided by, open brackets, minus 70.5 divided by 1,000, close brackets, equals, where's my pen gone? Equals 794.3, 3 sig figs throughout. So 794, well, is it 3 sig figs? Yeah, three or 2 sig figs is given. It's not a practical situation, so we won't mind too much. Minus 794 Kelvin. So the temperature is below 794 Kelvin, this reaction should be spontaneous. So I think we'll just leave it there, because I've got to the end of my time before I have to leave that. The mark scheme, make sure you use the mark scheme as well, have a look through, and we've covered the main things. Question 3 talks about Born-Haber cycle. So Born-Haber cycle is the big main concept that we haven't covered just be careful. Just be careful with whether you're doing a process once or twice. If you've got 1 mole or 2 moles, what is it per mole of? Are you being careful with every step, and are you being careful with state symbols? And you should be okay with 1 Haber cycles as long as you can